Okay. First, let me review actually last week's report, and was uploaded a little bit late. And first one is we have a two shaft connected in series, and the left and right hand side they are fixed, and the torque is applied at the junction, and the question is to calculate the angle of rotation V0 at the point we apply torque. Okay, that's the one question. And the second is to calculate the maximum shear stress. To calculate this maximum shear stress, you need to calculate the torque applied to each shaft. And then since it is a circular shaft, and I'm sure you have the equation which describe the shear stress distribution. And second question is a rectangular thin. Okay, this has to be thin. Doesn't look like a thin, but it is a thin. Thin means that this D0 is much less than this L. This is cross section. So anyhow, this thin wall shaft, rectangular shaft with a D0 and 2 times of D0 is subject to a torque, and we need to calculate the maximum shear stress. And let's say if shear yield strength is given tau yield, then calculate the maximum torque T0, which can be applied to this shaft without any material failure or yield. That was the second. And third one is this is a very important problem. The shaft consists of 2 different materials. One is the let's say material A and material B, and each one has the different radius, inner and outer radi. And then this shaft is subject to torque, and we need to calculate the angle of rotation, and we need to calculate the shear stress in A and B. To solve this one, the gamma is always the dp, dz, and r, right? dp, dz, and r. So this is a constant, and shear strain is proportional to a radius r. And this relation is independent of a material properties, which means that this equation is still valid or applied to this shaft, which consists of 2 different materials. Okay? And that means that shear strain is linearly varying like that. And then tau, shear stress, is defined as G times gamma, and G is a shear modulus, and which is not constant through the thickness, and this is a G1 and G2, and so let's say you would have this kind of shear stress and one material, and you would have discontinuous shear stress at the second material. Okay, depending on the G1 and G2. That's the key point here. Well, to calculate this phi, you should derive the equation. You should you should follow the torsion theory. And when you integrate the torque and tau and r and dA, and tau should go in there, and when you do integration of this and G should not be, G is different from different here and there. So that you need to be careful when you perform this integration. Okay, so what this should be sort of G1 and I1P and plus G2 I2P. And what do you have here? You should have dz, right? So what this you should have two different shear modulus and polar moment of inertia. Of course, this IP is corresponding to only this shaft, and this second one is corresponding to a second material. Okay. Any question on this homework? And this one is due this Wednesday, tomorrow night. Okay, today we will move to beam theory. Okay, we are still updating the lecture note, and this one is a little bit different from yours, but basically they are same. Okay, basically it's the same. And well, at the very beginning of this course, I always emphasize that the beam is the most critical structure. And last week we covered the torsion. Torsion is also important, but beam is always is a more important structure in general structure system. So now we are to study about the beam, and let us introduce a beam theory. And first, let's define beams. Well, this one shows some different types of beams. Okay, different types of a beam. Well, beam subject to some vertical load, subject to some concentrated moment, and supported with a simple support at two ends. And this one is especially called a simply support. Simply support means that only vertical force will be supported, not moment. And this one is the simply support. And cantilever beam. Cantilever beam means that at the left-hand side, it is the clamped. Clamped means that at this support, this boundary support the vertical load and moment. And this is the clamped, and the other end is free. And this is typically called cantilever beam, and subject to all kinds of vertical load or a bending moment. So a beam may be defined as a member, first of all, whose length is the relatively large in comparison with its thickness. Means that this length is relatively large compared to this thickness or cross-sectional dimensions. That's a geometrical characteristics for a beam. The most common types of a structural member is a beam, as I mentioned. So anyhow, in actual structures, a beam can be found in many different combination of size and shapes and orientations. Okay, types of a load applied to beam. What kind of a load is being applied to beams? Well, Just for the convenience of definition, we just introduce three types. One is a distributed load. Okay, distributed load. Distributed load means that this is not compared to a concentrated force and concentrated moment, meaning that we apply concentrated force at a certain point. So P unit will be Newton. And moment, you just we apply a concentrated moment, and unit will be Newton times meter and certain position. So these are concentrated force and concentrated moment. Whereas this load is not applied to a single point, is a distribute. Distribute, well, it doesn't have to be constant. It may vary like that. It may be a function of x. And so usually we use a symbol Q, can be function of x, and the unit will be a Newton per meter. Okay, Newton per meter means that, let's say if you want to calculate a certain force corresponding to this much, then you need to integrate from here to there to calculate the force. But again, the force is distributed from here to here, not just one single concentrated location. So this is called distributed load. Okay, these are types of load which we apply externally. And how about the types of support? Support. And this one, simply support, equals simply support. And always the boundary, it's simply support, it only support vertical force. So we only have a vertical force, and moment is a zero, meaning that simply support condition does not support any moment. It allows the rotation. It allows rotation. So after given certain load, the shape of the deformation can be like that. Means that this one is the rotated. Moment is always associated with angle of rotation. This is the, let's say, theta. And moment is associated with rotation. And here, as you can see, at simple support condition, the angle of rotation, we have the rotation because the moment is zero. And clamped means that we have two types of support, vertical force and bending moment at clamped. So the reaction force is always V and M. And the sliding conditions means that it allows travel freely move in vertical direction, but the angle, as you can see here, angle does not allow to change. So it may deforms like that, but this angle is still same. So in this case, the moment should be generate not to have any angle. And vertical force is always zero. But this is simple support and clamped condition is the two most important conditions. Well, this is just a summary of unknowns and boundary condition for different support. At the ends, we can always have either V or moment. So simple support condition, we have the displacement. Always the displacement is a 0, right? Because the simply supported means that the deflection is not allowed to have. To do that, we always have the unknown reaction force, supporting force. And how about the rotation? Well, angle, rotation is the allowed to change. So we have the unknowns. And moment, reaction moment is always 0. That is the for simply supported. And how about the clamped? Well, clamped case, we do not have any displacement. We do not have any angle of rotation. So 0 displacement, 0 rotation. To have these 0 displacement, we should have always the unknown forces. And sliding, well, we have a 0 reaction force is a 0, and this should be 0. Okay? It's a typo error. This should be a 0. And sliding, we do not have any angles, and the moment should be unknown. And how about the free boundary conditions? There is no support. Then always there is the 0 reaction force and 0 reaction moment. And the displacement and rotations are always unknown. As you can see here, any boundary condition, you have at least one unknown from vertical directions, and one unknown from rotational side. So at any support, you have 2 boundary conditions. Two types of boundary condition. One should be given in terms of vertical, either displacement reaction force or rotational angle or reaction moment. In beam case, we have y-directional, this is we call x and y. And x and y. And force equilibrium, always vertically we have a force equilibrium and moment equilibrium, z-directional moment equilibrium. So this is the 2 equilibrium equations. And remember, we have, when we calculate the reaction force in statically determinate problem in 2-dimensional case, we always have 3 equations. Fx equals 0, and Fy equals 0, and moment z equals 0. Those are 3 equations. And beam case, we do not need to, we cannot, this x directional force equilibrium does not give us any information, which means that we have 2 equations, okay, 2 equilibrium equations. So how many unknowns can we solve just by using this force equilibrium? Well, we can solve 2 unknowns. Okay, let's count how many unknowns do we have. Here, we have the vertical direction, reaction, and here another vertical reaction. So how many unknowns? We have 2 unknowns, and we have 2 equilibrium equation. So we can calculate these two reaction force. considering only force equilibrium. How about this one? This is the clamped, and at the clamped conditions, we have vertical reactions and moment reactions. And how many unknowns do we have? We have two unknowns, and using these two equilibrium equations, we are able to calculate those two reaction force. Okay? So this is the statically determinate problem. Statically determinate problem. Now, how about the internal force? How about the internal force? Well, here we just calculate a reaction force. And now, how about the calculate the internal force? Internal force means that, let's say we have a cantilever beam subject to a P at the end. And let's say, of course, we can calculate reaction force V0. V0 is should be simply P, and moment should be P times L. And this one again calculate from those two force equilibrium, both y-directional and moment equilibrium. And now question is that, as it says, internal force and moment. How much force, for instance, let's say we have a cross-section, arbitrary cross-section, and how much force, internal force, shear force, and how much bending moment will be introduced at certain section. Those are called internal forces. Okay, those are called internal forces. Internal forces or internal moment. How to calculate those forces? Well, again, we are using force equilibrium. Force equilibrium. Well, this should be a. So anyhow, we have a P here, and we have moment here. So applying equilibrium equation to here, we can simply calculate this and that, and okay. Well, this one, these two equation is to calculate this one. Okay. And this one goes to next pages. Internal force and moment. For instance, just for instance, let's take a look at the reactions at the position x equal half length. And we already calculated the V and M. And let's say we have a section at x equal to half length. Then how much the internal force, bending moment, and shear force will be generated here. The key point here is that, well, of course, this one is the from whole beams, and the question is the internal forces will be present at here. So to calculate that one, we have this one, which we will already calculate using force equilibrium, and then we just have unknown m here, and again we apply force equilibrium and moment equilibrium to this structure. So y-directional force is this V and this V0, and moment equilibrium, well, here we have the M here, and the length L/2 times V0 plus M0 equals 0. So moment should be like that. So this is the for given lengths, and if well, this is the same as the bottom one. And if this is the x, okay? If this is the x, well, okay, sorry. This one can be divided into two parts. One is this one, and this one comes to here. We separate them into two beams, and then the internal, at here can be calculated by two ways. One is the apply equilibrium equation to this part, and the other one is the apply equilibrium equation to this part. So again, this M and V, and force equilibrium is V and P. And moment equilibrium, this is moment here, and this P is causing also moment, and give us this much internal force. And as you can see here, this one and this one should be the same. So to calculate the internal force, this is the whole structure, and you just cut in half. And the internal force at this location can be calculated in two ways. One is the you apply equilibrium equation, this part, that's the one way. And second way, you apply equilibrium equation to this way, and you can get these two unknowns. Either this way, that way, and this one and this, they should be same, right? Action and reactions. And as you can see, the solutions are same. So if we summarize the internal force, when this whole beam subject to a P at the end, left hand side, the left hand side is clamped, and the reaction force, bending moment, and shear force is calculated from whole equilibrium. And then let's say we want to calculate the internal force at a certain section, and there are two ways. You can apply equilibrium equation here, or apply equilibrium equation here, and as you can see here, we have the internal force and downward, and here internal force should be upward, right? Because it's action and reaction, and here the moment is like that, and moment is like that, and minus and plus, they should cancel them out. Well, this is the a beam P, and at the section x equal to L/2. How about in another position, x equal some other position, arbitrary position? You can similarly calculate exactly the same way you did. And again, you can calculate this internal force at this section either from this equilibrium or equilibrium from this part. Okay, the answer should be the same. Well, this is just a review of the force equilibrium which we already studied in section chapter 2, right? So that is just equilibrium, application of equilibrium equation to a beam case, and then we calculate the internal force, shear force, first reaction force and shear force and bending moment. Now, we need to be careful about the sign. Well, here I didn't pay much attention to a sign. Here is the minus, and here is the plus and minus, and so on. Now we need to clearly define the signs for internal force. Actually, internal force means that shear force. Shear force and moment is the bending moment. Definition of a sign. Okay, this is the beam at a certain position X, and we have a cross section, and as we already defined this, once we cut, we have a two sections, two areas, and this area is the forwarding to plus side, and this one normal direction is in the negative side. So whenever we denote this area, we always say plus side, plus x, because it's looking at plus x side. And this side, this area is called minus x. Okay, this is the sign conventions for the cross-sectional area. Okay, this is just to remind. And now, definition of axial force, sign of axial force. Again, here, let's say this bar, this beam, or you may say, okay, this is the actually bar. This is just remind you of this sign convention in a bar, and this is the x and y, and this bar is subject to a tension. And then let's say we cut a certain section, and plus side, if we have a reaction force in the same direction as this area, we call plus. And minus area is subject to a minus force, then it's called plus, right? So if it is a tension, then this plus area is subject to a plus force, and minus area minus. So this is a plus. And same for this part. And plus, plus, minus, minus. But how about the subject to a compression? In compression case, and the minus surface will subject to a plus sign, plus directional force, and this plus force subject to a minus force. And same for here. So the compressive force, which we call minus force, will have different signs. Area and force, they will have a different. Plus area and minus force, and minus area and plus force, and so on. That was the sign convention for the case of axial force. Now, how about the beam case? Again, beam, we have two forces. One is the vertical shear force, and the other one is the bending moment. And shear force, let's say we subject to a upward, okay? This is the plus, right? plus x, and force is the, again, y direction plus y direction plus x and plus y directional force. And to have this beam in force equilibrium, at the left-hand side, we should have downward force to have force equilibrium. Am I right? So this one plus plus, and here minus minus. This is the called plus shear force. Okay, this is just definition. Plus x surface subject to y directional shear force, and minus x directional area subject to minus y directional force will be called plus shear force. In the other hand, if this one, subject to a different, this is a, the arrow should be this way, okay? Plus x subject to a minus x, minus y, and this way, and this way, and this is called what? Minus shear force. Okay, this is the plus x and subject to a minus vy, and this is called minus shear force. You have to stick to this sign convention, otherwise, you easily get confused. Now, how about the bending moment? Well, we also need to define a sign for the bending moment. And again, here is the plus x, right? And this is the moment, z-directional moment. Z-directional moment. Let's say we apply the z-directional moment here. To have a moment equilibrium, we should have opposite. Okay, this is this moment, and this should be this moment to have a moment equilibrium. So let's say this is the minus directional moment in minus x directional surface. So minus moment z at minus x directional surface, and plus x directional surface, you have a plus z directional moment, and then this is called plus bending moment. Okay, this is the subject to a plus bending moment. So plus bending moment always causing curvature in like that. I mean, deformed shape will be like that. And the other hand, this is the just opposite. This is the plus x subject to a minus moment, and this is the minus x, this is the plus moment z. Then this will deform like that, and this is called minus bending moment. Okay, minus bending moment. And again, this just showing the internal forces at arbitrary cross section. Okay, again, you have to understand this sign. This is the rules. Okay, rules for signs. Okay, now with this sign convention, let's try differential equation. What is differential equation? Well, we will drive a equilibrium equations for beam. This is the first step of derivation of a beam theory. Let's say we have a beam subject to an external force. External force, which is denoted as Qx here. Force per unit length. Okay? Force per unit length. And Q can be any function of x. Now we are looking at how this internal force and moment should distribute inside in this section. There must be some relation. There must be some equation which governs the distribution of internal shear forces and bending moment. That is the called beam differential equations. And we are looking at this dx. Okay, dx. This is the dx. And this is the position x. So at the x, this is the at x, and this is the at x plus dx. And this surface is the negative x directions, and we assume here we have a Vx shear force, and this is the bending moment, Vx and Mx. And now here we have shear force Vx plus some increment dV, and moment we have also some increment dm. This dm and dv is caused by some distributed load, this qx. Within this dx, we have a certain distribution, external force. And now let's apply force equilibrium and bending moment equilibrium to this structure. Okay, this beam with this length. At the left hand side, we have this much force, and the right hand side, we have this much force, and between these two ends, we have distributed external load. Now we should be able to drive equations from equilibrium. Okay, so let's take a look at right down here. First, y-directional force equilibrium. What is the y-directional force here? Y-directional force is this one, right? Let's say y-directional force is this one. And y-directional force is what? This one, right? And what else? Yes, we have another y-directional force applied to this part. So all of these y-directional force should be in equilibrium as dx, that is minus or plus. Yes, it's the downward. Of course, that is minus. Right hand side, we have a plus Vx plus dv. That's the plus. And then Qx, how do we calculate the force out of this distributed load Qx? Of distance, right? Dx. So assuming that within this dx, this Qx is assumed to be constant. So this needs to be 0. And as you can see here, this Vv disappear, and simply dv dx plus q should be 0. Well, very important differential equation, which means that whenever you have the q is given, you simply solve this differential equation to have this v as a function of x. Okay? So if q is 0, there is no q, then v means what? V is constant. All along the x, there is a constant. If there is no q, v is a constant. Well, anyhow, this is the one first differential equation which governs the distribution of shear force. Now, second one. Second one is the moment equilibrium, right? Moment equilibrium. How do we calculate moment equilibrium? Let's say, let's count. Let's say, let's denote which one is the moment. Well, this is the moment, right? This is the moment. And this one is the also moment. What else? Well, when we consider moment, we always need choose a one point, a point with respect to this point, we should calculate some moment. So let's say we choose this point. You may choose any point. Let's say we choose this point. Then this force, this shear force, will cause a bending moment, right? And this shear force will just go through this point, so there won't be no moment. And how about this distributed load? Well, there seem to be some moment. Let's list them with respect to this point. Okay, so okay, sorry, this sign is this way, right? So moment, and we have the minus m here, and plus moment plus dm, which comes from this. And then this shear force, okay, V plus dV times dx. V plus dV times dx would cause a bending moment. And what else? Well, this Qx times dx, which will be a force, and then let's say you have some distance. This is the resultant of a force from this qx, and then you multiply some distance, which is the half of dx. This should be 0. Okay? Now, while this dx is approaching 0, if dx approaches to 0, this term is simply disappear. And if you pay attention to each term, this is a dm, this is the v dx, this is dv dx, this is a dx dx. So when dx goes to 0, and these terms and this term will disappear. The only term left will be dm plus v dx equals 0. And here we have dm dx plus v equals 0. Now, this is the second equilibrium equation from consideration of the bending moment. Okay, bending moment. And take a look at this term and this, and they look very similar, but here we have a v and q. This is the moment and v. Just we have a first order differential equation, and again remember this is the force equilibrium, this is the moment equilibrium. And next page it just shows you again the one we just derived. This and this. Okay, those are two equilibrium equation. And here, if we eliminate the v, just eliminate the v here, and then we can have the m in terms of q. Right? We put this into here, then v will be gone, and moment in terms of q. So again, q is the externally given as a function of x. If you integrate twice, you will have the moment distribution. Or you can have a step by step. Q is given, you calculate the v, and once you have a v here and put it here, you calculate the moment. And moment distribution and v distribution is the key part. Well, I will back to this singularity later, and let's just review the equilibrium equation we just covered. And dv dx plus qx equals 0, and dm dx plus vx equals 0. And now let's say we apply this one to this simple cantilever case. This is a P, and this is the cantilever case. And let's use this equation to calculate a internal force Vx and moment x. Okay? Again, the purpose of derivation of this one is that now we can calculate internal force, shear force and bending moment in a beam as a function of x. For any types of a beam, we can calculate. We don't need to consider any other equilibrium. All we need to do is just solve this differential equation. Okay. What is the Q? First of all, what is the QX here? QX. From here to here, QX is 0. This is very important. QX is 0. There is no externally applied. Oh, how about this one? Well, this is the applied at the end. Is a boundary conditions. So do not consider this one as the QX. As you can see here, QX is simply 0. If QX is simply 0, then from this first equation, dV dx equal what? 0. And which means that V equal constant. Now it says V equal constant. Means that the shear force we know is at the end. So let's say V x equal L. What is that? Right, P. But is it downward? Should be minus. This constant, it is constant, but that constant value should be minus P. Which means that any cross sections, okay, any cross section, the shear force should be minus P. Now, use how to calculate the moment distribution. Using the second equation, dm dx, Vx is the minus P, so it should be P. So let's calculate the moment. Moment just integrate, and Px plus constant. Yes, constant. There's integration constant. This is the equation. And how to calculate the C1? Well, the moment here at the end, how much the moment here? It's simply 0, right? No external moment is applied at the right-hand side, which means that at x equal L, the P times L plus C1 equal simply 0. So the C1 equal minus PL. So I will summarize here. Vx is simply minus P, and moment x is simply P x minus L. That is the internal force distribution. Those are internal force, shear force and bending moment as a function of x. Which should be same as the one we obtained from this condition. At x equal L over 2, we simply have this P and this one, right? And back to that equation, we have the same one here. P, and if x equal to L over 2, then moment is simply m times minus L over 2. Okay, those are So what we cover here is that we have a beam, okay? We can calculate the internal forces or reaction forces considering two equilibrium equations. One is the vertical shear force and the other one is the z-directional bending moment. That we need to understand that. Now, to drive the internal and bending moment at arbitrary x positions, we have differential equation, two differential equations. Each one governs shear force and bending moment respectively. So we can just simply use those two differential equations to have internal force and bending moment as a function of x. Okay? That's what we have covered here. And singularity function, I will back to here later. Any questions so far? Let's try a little different cases. Okay, I will give you a one case, which is Q0, constant distributed load, Q0. Well, unit should be Newton meter. Now, let's calculate Qx and moment x. You do it now. And remember there's a differential equation, and one is the governing shear force, dv dx plus q, x equals 0, and the other one is dm dx plus vx equals 0. Okay. So this kind of question will be typical problem you should be able to solve. And here is the solution. Simply Q0 in general sense is a function of x, but here is given as a constant, right? So from this equation, dv dx equal given as minus q0. q0 is a given. And integration give us minus q0x plus c1, right? And the point is that how to calculate the c1. See here, the shear force and or bending moment. Do we know shear force at this point? Well, there is some unknown V and unknown bending moment, which is unknown, right? But what we know is that shear force is 0 at x equal L, right? And moment is given as a 0 at x equal L. Those are two conditions we can use to solve this differential equation. You may say, oh, there is a certain shear force at that point. How come it's a 0? Well, this is not a shear force. That is partly a shear external load. At the end, there is no shear force. Okay?
I think we grab
So I will get back to there. So we have these two conditions, and if we integrate them, Q0 is constant, and we integrate minus Q0 plus C1, and using this condition, and L here, then C is simply Q0 L, right? So Qx is given QL minus X, and right, this is not right. This V should be here. X equals 0. V equal what? Q times L plus, and should disappear like, decrease like that, right? This is the shear force diagram. Shear force diagram. And this is the bending moment diagram. Well, for the bending moment, we have this differential equation, and we put this equation into here. We have the V here, and then we simply integrate them. And then, again, we have a different integration constant, C2. How do we get this C2? Well, we have the condition, moment equals 0 at x equal L. So from that condition, we can get the C2. So if we put these things into here, then we can get the moment like that. Right? Okay, so for this kind of case, we have a shear force like that and bending moment like that. And here you need to pay attention to a result. Okay, V is a constant. Then shear force is always linear function. You can notice that from this equation. See, derivative of V is always Q. So Q is a constant, then V means linear function. If V is a linear function, then moment is quadratic function, right? Because you need to integrate one more time, and you will have the square term here. And previously, in this case, subject to P, then the V is what? V is a constant. That's right, constant. And moment is what? Linear function like that. Starting from minus here and then positive. See, positive here. So Q is a 0. That means V is a constant. And V is a constant, then moment is always a linear function. That's really good to know. See, if you have a very much complicated load distribution like that, sometimes you have a force here, 0 here, and some force here like that. Each regions, for instance, here, you don't have any Q, then you should have a V is a constant and moment is a linear. And this is the linear, then shear force will be quadratic, and moment will be and triple, right? And something like that. You always, when you integrate, you will have a order, increase one order. Okay, that was for the equilibrium equation for the beam. And again, there are always two internal forces. One is the shear force, and the other one is the bending moment. Those can be calculated from given distributed load and boundary conditions. Okay, so that will complete today's class. And any question? Okay, I'll see you Thursday.